Hi, welcome to the multivariable regression class in our regression data science course on Coursera. My name is Brian Caffo. The course is co-taught with my collaborators Roger Peng and Jeff Leek. We're all in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health. If I were to give you a example where I said there was a regression relationship between breath mint usage and pulmonary lung function, let's say measured in FEV, which is a measure of lung function. You would be skeptical, right? Because why in the world would breath mints be associated with lung function? And then you would say, well, maybe, smokers tend to use more breath mints than non-smokers. Maybe what you're seeing is some sort of indirect effect of breath mint usage, that the really direct effect is smoking, and that's probably the culprit. And then if I were to return and say, well, I really believe that there's this honest-to-goodness breath mint effect, what would I have to do to convince you? And you would probably have to say something like, well, imagine if you just looked at smokers by themselves and there was this effect. Or if you looked at non-smokers by themselves and there was this effect, then I would be more likely to believe you, or at least you would have eliminated my concern that smoking was the culprit. I still may not believe you because there doesn't seem to be any scientific basis. Okay, but in other words, the idea is that, well, at the bare minimum, I would have to demonstrate the results hold with smoking status held fixed. Another example of how you might want to use multivariable regression. So an insurance company is interested in how last year's claims can help predict a person's time in the hospital this year. So they want to use the enormous amount of data collected in claims to predict a single number. But linear regression really isn't equipped to handle anything more than one predictor. And how can we generalize linear regression? How can we generalize linear regression? There we go. How can we generalize linear regression to incorporate lots of regressors for the purpose of prediction? And then, what are the consequences of doing it? If we throw a lot of regressors into a regression relationship, what are their consequences? Surely there must be consequences to throwing variables in that aren't related to y, and surely there must be consequences to omitting variables that are. Okay, what are those consequences? What happens? So let's talk about the linear model. So the general linear model, I think you guys probably could guess what the general linear model was from simple linear regression, that all we do is add terms, right? So here was the, say, linear part of regression to the origin with the error, was the regression to the origin version of linear regression, and we might add an intercept. But the general linear model just adds these extra terms. And of course, there is there is an intercept embedded in there, in that perhaps one of these let's say ji's, if it's just perfectly constant, right? If it's just one, then that term would be an intercept. And we can write the general linear model as this way, so we don't have to write a bunch of pluses out. Okay? And so how could we get estimates? Well, we could do least squares and just try and minimize the distance between the observed responses and the predicted responses given the linear model squared, and treat each one of those squared residuals equally and try to minimize the sum of the squared distances. That would be reasonable. And then, just like in linear regression, under a correct additive model with Gaussian errors, the least squares criteria also winds up being the maximum likelihood estimate. And we're not going to show that. You can show that if you'd like. And notice linear, by linear we mean linear in the coefficients. If we include x1 squared, for example, as a regressor, that really is just another x, right? That really is just x. We just happen to square it in the notation. what we really, if we were to put it into a computer program, we would just put in the squared versions of x's, and the computer program wouldn't know that they were squared, right? What's really meant by linear is linear here in the coefficients. So anything that's linear in the coefficients is a linear model. So in this case, we've just squared it. So we could have a model that says y equal beta 1 sine x, right? Where sine, I mean the trigonometric function sine. That's still fine, where this is still just a model y equal to beta 1 z, where z is the, say plus air, where z is sine x. If you sine a vector and then put it into the computer versus versus just put in z, the computer doesn't know the difference, right? So what's linear, what's important about it being linear is that it's linear in the coefficients. So how do we get estimates? Well, if you really want to take a linear models class, go take a real honest-to-goodness linear models class. And what I'm going to go over is an intuitive development that teaches you what the multivariate adjustment kind of does, and it develops the estimates along the way. And again, we won't require linear algebra, we won't require calculus. I do want to remind you of this one fact. If we have a model that says, if we have a model that just said, darn it, let me just try one more time. If we have a model that says yi equal to xi beta plus error, the regression to the origin model, the estimate, remember, worked out to be that, summation xiy divided by summation xi squared, okay? And now let's just extend that model to two regressors, right? So that the expected value of y includes an xi1 and an xi2. And I noticed I'm sometimes confusing whether I write 1i or i1 like that, but I'm hoping you'll be able to figure that out. I'll try and correct it so that it's consistent on the GitHub repository, but when recording the lecture, I've noticed a couple of mistakes like that. I'm hoping that won't cause any confusion. So remember that, just going back to our regression estimates, when we developed the least squares, remember that if mu I hat, where mu I hat was equal to xi1 beta 1 hat plus xi2 beta 2 hat, right? If mu I hat satisfied that equation for all possible values of mu I, right, mu I being right there, then we found the least squares estimates. Well, okay, and that's why we did it that way when we did linear regression, so that we could just use the same equation here. Okay, so there's our equation. Now let's just plug in to the mu I and mu I hat as to what they are. And you wind up with this statement right here, right? yi minus beta 1 xi1 minus beta 2 hat xi2 times this guy. But notice we could multiply this times this, and then this times that, and we would get two equations, summation yi minus beta 1 hat xi1 minus beta 2 hat xi2 times xi1 times a beta 1, I'm sorry, beta 1 hat minus beta 1, and then the same thing with a beta 2 hat minus beta 2 and an xi2 out there. If that term is equal to 0, and this one with the 2's on everything is equal to 0, then this whole expression will be equal to 0, okay? And so what I've done is I've simply rewritten these two conditions right here. And hopefully you'll have noticed a pattern that in general, for the more than two variable case, you just have, if you have p variables, you have p of these equations. So how can we solve these equations? Well, we have two equations and two unknowns, right? We don't know beta 1 hat and beta 2 hat, but we've got two equations, so hopefully we can solve it. So if we take equation 2 and hold beta 1 fixed, right, then and solve for beta 2, we get that thing, right? Churn through the work. And then you can take beta 2 hat, which is now just written as a function of beta 1, and plug that into there, and then we get another equation. We get another equation that we can solve for beta 1, okay, because it only has the one variable. And you can rewrite that equation so that it is exactly nothing other than, so let me go back one again just to focus on this equation. Notice, what is this? Let me get it better. This. So this guy right here, this term right here, is the slope estimate from the regression through the origin model of yi equal to x xi1 times beta 1, let's say, plus error. That's the regression to the origin estimate for that. And then if we were to multiply that times, I'm sorry, with the 2, it was the regression through the origin estimate for yi equal xi2 times beta 2. If we were to then multiply times xi2, we would get the predicted y from the model, yi equal to xi2 beta 2 plus epsilon I, right? So this term is the predicted y from the regression through the origin model with y and just x2. And so this is the residual from the model that only includes yi and xi2 by itself as a regression to the origin. Similarly, this right here, right, is exactly the residual for the model xi1 equals xi2 times whatever, I don't know, let's say gamma plus epsilon I, right? And then when we multiply it times xi2, we get the predicted version of xi1, and then we subtract it from xi1, we get the residual. So what we can do is we can write that equation as the ith residual if we were to have regressed x2 out of y minus beta 1 hat times the ith residual should we have regressed x2 out of x1. Okay? In both cases, regression through the origin. And we can then just solve this. And here I give the equation for what how I define the residual for two vectors A given B, right? And so you get the solution beta 1 hat is this, which is again regression through the origin. It looks like the regression through the origin estimates, though if we were using the residuals instead of the vectors themselves. But we have this x1 here. But we're going to deal with that right now. So remember, so just from our definition from the previous page of what the residual is, this residual of x1 having regressed out x2, if we square it, right, that's this residual times this guy, just applying the definition. And I'm missing a sum there. Sum I equal 1 to n. So then distributing across the sum, we get that guy, and then we get this guy right here. Okay? But I hope you recall that when we take the sum of the residuals and we multiply them times the regressor, sum of the residuals times the regressor, that equals 0. We discussed that in regression. And if you don't believe me, plug in and convince yourself that it's true. So, so that guy, right, I'm sorry, this guy right there is 0. So what we get, just plugging into the equation, is that this guy right here is equal to summation of the residuals times xi1. And so what we can do is, just going back, we can replace this denominator right here, right? And we can replace by this equation right here, we can replace it by that. Okay, as a result, what is this? Well, this is just equal to the sum of sort of vector 1i times vector 2i divided by the sum of vector 2i squared, which we agreed was the slope estimate from the regression through the origin, where vector 1 is the response and vector 2 is the predictor. Okay, so let's summarize that. Summing it up. So let's sum up fitting with two regressors. When we have two regressors, the regression estimate for the slope of the first regressor is exactly the regression through the origin estimate, where we've regressed the second regressor, x2, out of y, and we regressed the second regressor out of x1. Okay? And so that makes a lot of sense to me, because it's like removing x2 from both y and x, and then only considering x1 in isolation and y in isolation, with x2 having been removed from both. So I think that's interesting, and it gives us a good way to think about what multivariate regression is doing. Also, I would add, when xi2 is the coefficient for it is exactly what you would get from regressing x1 out of y and x2, okay? Because there was nothing particular about choosing beta 1 to look at. We could have looked at beta 2. Okay, so we've actually done a case with two variables. Simple linear regression is an example with two variables, where here we specify our model. I'm going to specify it a little bit differently than we normally do, in that I'm going to specify that the second regressor is just a constant 1, is an intercept term. Okay? Then let's look at what happens here. Then look at what happens when your regressor is an intercept term. If x2 is just 1, just plug in 1 for there and there, then you wind up with, then multiply it times x2i, which is also 1. Replace 1 in all those three occurrences, you get that you wind up with x1 bar. And so the residual, having regressed out the intercept by itself, is nothing other than the centered variable. And similarly, there was nothing particular about choosing x1 to do first. We could have done y first. If we regress x2 out of y, we get the centered y variables. Okay, so regressing the intercept out of a variable, it turns out to just be demeaning the random variables. Okay? And so our beta 1 hat works out, I said, is this equation, those residuals. If we plug into them, then we get exactly the formula that we know and love at this point. Okay, so we've already done one example with two regressors. Now let's do general regressors. So I struggled a lot with trying to get a way to do this without doing any linear algebra, and I think I have a nice treatment. So let's go back. Hopefully you remember what, went too far. Hopefully you remember, let's see, there it is. Hopefully you remember these two equations, in that to get the least squares estimates, we said if we could get those two equations to be 0, then we'll have the least squares estimates. And it wound up with two equations with two unknowns, and look where we got it from right there. I'm hoping that you will believe me that if we have more than two regressors, we wind up with just a series of equations exactly like that. And that's what I have right here, is that we need to find a set of equations that satisfy the root, that satisfy this root that we need. Okay, and so what this winds up with then is now p equations and p unknowns. Okay, and solving them yields the least squares estimates. But if you want a good, fast, general solution, then you need to know some linear algebra to get a general solution. And if you want it to be fast, you need to know some numerical linear algebra. But this point is interesting because it just generalizes what we did for two variables. The least squares estimate for the coefficient of a multivariate regression is exactly regression through the origin with the linear relationships of the other regressors removed from both the regressor and the outcome by taking residuals. And because all we've developed is how to take residuals one at a time, you can do this one at a time, removing the linear relationship of x2, then x3, then x4, and x5 to get the adjusted relationship between y and x1. And it doesn't matter what order you do it, you just have to do all of them from both the y and the x1, and you'll get the multivariate adjusted case. So what that means is, in this sense, multivariate regression adjusts a coefficient for the linear impact of all the other variables. We've removed the other variables from both the regressor and the response. Which also tells us that if we'll see that there's then a special case if there is no relationship between a regressor and its the confounder that we're trying to remove. So again, this is another one of these details where you won't be quizzed or tested on, but I wanted to just show you how you get these things. So remember, we have these set of equations, and imagine if you held the first p minus 1 beta hats fixed, then you could solve for the pth one and you would get that estimate. And then if you plug beta p hat back into all these other ones, right, plug it in right there, then you wind up again with all of the residuals, ei of y given xp and so on, having regressed x of p out. But again, we have this guy right here, okay, x instead of the residual. But let me just show you that consider that equation right there. If we just reorder the residual definition, right, we get that equation right there, just reordering. Okay, and a fact that we've used often is that the sum of the residuals times the regressor is 0. Okay, so combine these two facts. So what we could do is for xk here, we could replace it with this expression right there. And then this expression, this part, is constant, and then this x sub p part varies. However, all of these residuals are given x sub p, and given that equation, when summed over, it goes away. So really, as far as this sum and all these residuals are concerned, we can just replace this x sub k by this x sub k given p, the residual given x sub p. Okay, so the long and short, let me move on to the next page. And if you're really interested in the details, you can go over the mathematics with a fine-tooth comb. But here's the end result. We've reduced p least squares equations now to p minus 1 least squares equations and p minus 1 unknowns. And then in that process, if you look at this equation, right, these sets of equations right here, wrong one. Let me get it. If you look at this set of equations right there, it's exactly the least squares equations again, but only p minus 1 of them instead of p of them. And instead of y and a bunch of x's, it's the residuals of y having x sub p removed, and all the x's having x sub p removed, the linear relationship with x sub p removed. So we're at the same set of equations, but instead of having p of them, we have p minus 1 of them. And then you can just keep doing this process. Then you have p minus 1 of them. You can do it again and get down to p minus 2 and so on until you're down to the one adjusted effect that you want, and then you have it. So in other words, think of it as follows. If we want an adjusted relationship between y and x, keep taking residuals over confounders for both and do regression through the origin. And I would just say the order, once you remove the linear association of y, then x is the same as removing the linear association of A then B is the same as removing the linear association of B then A, so the order doesn't matter. And we know that. We can prove that. It doesn't matter because our choice of doing P first in that equation was arbitrary. And I would just note, this isn't a terribly efficient way to get estimates. It just shows how to do it without using any linear algebra. But you can get it in a more efficient way. But let's actually do it with R just to prove to ourselves that it's the same. So here I've generated 100. X is random normal, and then x2 is random normal, and x3 is random normal. And I want my y, all my slopes are just 1, and I have an error term of 0.1. And I want the relationship between y and x having gotten rid of x2 and x3. And because I don't want to just keep taking residuals, why don't I just define my residual function as it takes a and b, and then it's the residual of a having regressed out b. So a minus sum a times b divided by sum b squared times b. And so my residual of y, if I want to get rid of both x2 and x3, I would take the residual of y, taking out x2, the residual of x3, taking out x2, and then take the residual of that whole thing again. And that would be the residual of y having taken out both x2 and x3. And here's the residual of x having taken out both x2 and x3. I'll take out the residual of x2 and the residual of x3 given x2, and then I'll take the residual of x with x2 out and the residual of x3 with x2 out and the residual of those two, and then I'll do the regression through the origin slope, and I get 1.04, right? Now, notice I didn't include an intercept in this fit. So if I'm going to try and show that it agrees with R, I need to remove the intercept. So I'm doing coef LM, and I'm going to remove the intercept just so I'm fitting the exact same model. And notice it gives me the same number. R doesn't do it this way. It does it a little more efficient way, but it just shows you that it gives you the correct answer. I just want to show quickly that order doesn't matter. So here I reverse the order here and look at how I define these EX and EY. Look at how I defined it now. I do x3 first, and then take the residuals again, and I get 1.04 again. Okay. And then also, let me just show that you could do this in R by, let's say, take the residual of y having gotten rid of x2 and x3, and the residual of x having taken out x2 and x3, and then do your own regression through the origin, or you could do LM minus 1, and you get the same answer. Okay? So again, just showing that adjustment is the process of iteratively taking residuals. Let's go over how you interpret the coefficients real quickly. So again, my expected value of my y, given a particular set of values of the regressors, is exactly this relationship, right? We've gotten rid of the plus e part. So imagine if you take this first regressor and you evaluate it at x1 plus 1, holding all the rest of them fixed at their values, versus this guy where x1 is held at x1 by itself. That is this equation is this guy right here, and this equation is just that guy right there. Do the arithmetic, and it works out to be beta 1. Okay, so what did we do? So all we did was increase x1 plus 1. So the interpretation of a multivariate regression coefficient is the expected change in the response per unit change in the regressor, but the important part, don't forget this part, holding all the other regressors fixed. Right? So if we're adjusting for smoking status, it's like we're holding smoking status fixed. Again, we're assuming that the relationship between the response and the regressor is constant across smoking status, right? Because we haven't put in any interactions, but that's the idea of what regression adjustment is doing. So let's go over a couple other odds and ends just so we know. Our model is this guy plus the error. We tend to assume our errors are IID normal 0 sigma squared, at least in this class. Our fitted responses are nothing other than putting the fitted coefficients in. Our residuals are just going to be the difference. Our residuals are going to be the difference between our fitted our fitted y and our actual observed y, our variance estimate is just going to be the average squared residual. We're going to lose some degrees of freedom for all the parameters we had to estimate. We had to estimate p slope parameters, so we divide by n minus p instead of n, but it's still, this shouldn't be a great leap from what you already know and do from linear regression. To get predicted responses, we're just going to plug them into the model. We have a prediction interval. It's going to have a +1 if you want a prediction interval, and it's not going to have a +1 if you want the confidence interval for the prediction surface. Coefficients have standard errors, right? And the standardized coefficients, these guys, beta k hat minus its true value divided by the estimated standard error, are going to follow a t-distribution with n minus p degrees of freedom. And then again, the predicted responses of standard errors, so we can calculate expected response intervals. So it's all the same as simple linear regression. So it's sort of like you did some training, some drills on simple linear regression, and now we're at the main event, linear models, and you're seeing how most of these ideas extend very easily. So let me just sum up linear models, because I think linear models are very important. In fact, I think linear models are so important that I would call them the most important applied statistical and machine learning technique by far. That nothing else even comes close. And I'll just name off the top of my head, when I was writing these slides, some of the amazing things you can accomplish with linear models. One thing is you can decompose a signal into its harmonics with linear models. And I'll do an example of that just for fun later on at the kind of end of the class. But the so-called discrete Fourier transform is nothing other than a linear model. Now, granted, you can fit it a lot faster than especially than the way we taught today, but it's nothing other than a linear model where your x terms are a bunch of trigonometric terms. So we can decompose a signal. For example, you pluck a guitar string at A on the A string and record it, digitize it, chop off so that you just get where the string is playing the A, pass it through a linear model with the correct terms, look at the squared coefficients, and you'll find the one at the perfect frequency of 440 or whatever it is for A will be the one that's significant. Okay, you can flexibly fit complicated functions, right? So if you have data that look like this, like that, and you want to fit something that's not that complicated, but you want to fit something like that, let's come up with something more complicated, something like that. You wanted to fit something like that, you could do it. You can fit factor variables, so like a treatment effect, as predictors. You can uncover complex multivariate relationships with the response, and you can build accurate prediction models. Granted, a linear model is not going to do as well as some super complicated random forest model or whatever, but it's very interpretable, right? Linear models are wonderfully interpretable. So if you're going to stray away from linear models for some complicated machine learning technique, you're giving up a lot of interpretability for probably for better fit, but you may not be getting that much better fit for the trade. So they are great technique to learn. I think they're wonderfully important, and they have so many amazing applications, and that's why you find, basically either linear models or maybe statisticians have rebranded linear systems, but you find them rediscovered in all different sorts of engineering and mathematical fields. Because the idea is just the idea of decomposing things into a linear system is just an intrinsically useful idea. So we'll cover lots of different ways to utilize this kind of model in this class.